we have been mostly focusing on high-level system modeling and control for electrified powertrain, right? Today, we're going to shift our gear towards a little bit different topic, which is engine start control. And you can think of this as a low-level control, and there are many problems, many low-level control problems that are in this field. I mean, for electric powertrain in general. So you can get a feel of what low-level control looks like. But even though this practically this is a low-level control, meaning that it requires feedback control theory and application of that. But in this course, in this lecture, I'm going to use optimal control theory applied to this lower level control. So this is going to be a bit of a mix of low level control problem solved by or coupled with optimal control problem, which is usually applied for high level control, because usually optimal control theories are more applicable to trajectory optimization, or especially when it comes to DP problem. Course of dimensionality is a major problem. So let's take a look. So this lecture consists of 3 parts. The first is going to be the modeling, the model for engine start problem. And the second is the application of optimal control theory or dynamic programming for engine start problem. And then third is going to be how we can actually design a practical controller based on knowledges and results we obtained from dynamic programming. Okay. The problem. This is the problem. Okay. So we have P2 hybrid, which has this electric motor located between clutch and transmission. This is usually pretty cost-effective or easy to retrofit system, because you still get to use existing transmission, and you only need one motor and battery. So that's another plus. But one of the major drawback of P2 hybrid is engine start problem. Because, so I don't know if please try to visualize what's going to happen when you go from EV mode to hybrid mode. So when this powertrain is running in EV mode, the clutch is disengaged, so you can neglect engine, right? Engine is not moving at all, and then electric motor is going to be driving the vehicle, right? But then driver is now asking for high power, which electric motor cannot provide. Or if vehicle is now moving at a faster speed, which is going to require higher power at higher speed, so then you need to start the engine, and meaning that you need to move from EV mode to hybrid mode. And in that case, you need to somehow start the engine, right? Because when engine is not moving, when engine is not rotating, engine cannot self-propel, right? Unlike electric motor. Electric motor can provide torque when speed is 0, right? But engine cannot do that. And engine needs to start rotate, and then you can put fuel in, and then you can fire, right? So you need to bring engine speed up to a certain level, from 0 to say, 700, 800 RPM or higher. How are you going to do that? Existing conventional powertrain has a dedicated engine starter motor, which can also work as a generator. I picked up that, okay? Usually there is a small engine starter motor, and then you have a separate generator for generating electricity, okay? But because P2 has this challenge of how to start the engine, in theory, you could start the engine using this clutch, right? For instance, you can start engaging this clutch, and then so this was rotating, right? But engine side was not rotating. And if you start engage, put pressure on the plate, and there will be friction, right? So there will be torque and power transferred to the engine, because this side is faster than this side, right? So now engine speed will start to ramp up, right? And eventually it will be synchronized, right? So speed of this side will be synchronized with speed of this side, right? And then you can lock up the clutch. Then you're done with engine start, right? And then you can fire and everything, right? And now engine will provide power to the drive line, right? And then now you have more power from the engine and motor, right? But until that point, until engine can provide power using fuel and firing, you need to consume energy. You need to put energy into engine to start the engine, okay? And because of this, but by the way, this seems reasonable, right? This seems solvable, but in practice, this is quite challenging, because controlling this clutch accurately is challenging. Plus, if you want to start the engine fast, you need to apply large pressure so that engine speed ramps up fast. But if you do so, you are taking a lot of power and energy from the motor and battery to start the engine. And what's going to happen if you do that is that you have this power demand from the driver on the wheel side, right? But if you use all of the motor power for starting the engine, then you don't have enough power to meet the power demand, right? Are you guys following? Any questions? So this is pretty tricky problem, right? You have limited amount of power from the battery and motor, and you need to provide power to the wheel, and you need to start the engine, right? And you need to control clutch properly, okay? But if you slowly start the engine using low pressure clutch, then what's going to happen? Well, then you may not experience a lot of torque hole, or you can probably meet get close to power demand, but because engine start is delayed, passengers will not be comfortable with that, right? Or if you ask for high power demand, then you cannot meet that power demand for a long time, right? If engine start is delayed. So there's this dilemma of how much should you provide power to start the engine, You want to start engine fast, but if you do so, you cannot provide any power to the power demand, right? To the wheel. So this is a tricky problem. So to mitigate this problem, Hyundai Motors actually put extra motor here. So that they have a separate, dedicated motor generator, okay? So they can start the engine, and which is motoring, right? If you want to start the engine, you need to motor. You have to put positive power into the engine. But then you can also use it for a generator. Then this can work as a series hybrid, right? If clutch is disengaged, you have this generator, you have this motor, right? But then the problem is that now one of the main advantage of P2 or parallel hybrid was having only one motor, right? But if you have second motor, then there's no, that benefit, right? So this is what Hyundai Motor is experiencing. So one way to overcome this is that how can we start the engine using this clutch and motor without second motor, right? So can we solve this using control theories, right? So that's where this project started, okay? And in addition, when you apply pressure to the clutch, unless you apply very controlled manner, this applying pressure on the clutch will also lead to reaction torque, right? Because if you start the engine, apply clutch pressure, then that's going to create disturbance to the driveline, right? Resisting torque. So from passenger perspective, the wheel perspective, the amount of power and torque applied to the wheel must be relatively steady, right? But if you don't carefully control clutch, you may experience torque fluctuation, right? And you may feel like this, right? And that's not good for products, right? That's not acceptable. So that's another control problem, right? And that problem falls into noise, vibration, harshness. And in this lecture, we're not going to, the scope of this project is not going to handle these NVH issues, okay? So that is this. So we are going to focus on drivability rather than NVH, okay? And that's because we wanted to explore, we wanted to investigate the full potential of the engine start problem. You know, how fast can we start the engine? You know, and what should be the optimal control strategy? Do you start to see some similarity between this problem with you know, fuel economy optimization problem? So this was the problem formulation I had to go through. This was part of my dissertation, and you can see how we tried to formulate the problem so that the problem can be handled by optimal control theory. Okay, but in practice, you do need to handle NVH problem. Okay, so if you have disturbance, you need to be able to reject that, and you need to somehow smooth out the output torque. You know, that has to be handled by the feedback control you know, theories and applications. But here, if we focus on drivability, then we can formulate this problem into an optimal control problem. And now we're going to start with modeling. So everything seems quite similar to what we have been dealing with so far. So we have P2 hybrid, we have all the components and everything. But here, the focus shifts a little bit, right? So before, you know, so we had to model battery, right? Because of battery state of charge is important. But here, we're not focusing on the efficiency, right? We're focusing on the drivability. So we don't really need to model battery, right? Instead, we need to develop more accurate engine model. In efficiency fuel economy optimization problem, we modeled the engine as a quasi-static map, right? But in this problem, we are looking at shorter time horizon. So when you start the engine, we're looking at like you know, less than 1 second, right? So we are looking at you know, faster dynamics, okay, rather than slow dynamics. So now we need to start considering slower dynamics that are present in these components. And engine does have relatively slow dynamics, okay? I mean, fast dynamics. Electric motor, clutch, transmission, they all have fast dynamics, but compared to engine, they're even faster. So some of that are assumed, very, very fast. Okay. So anyway, so with that in mind, let's take a look at this model. So the engine start model looks like this. This is the overview of the model. Okay. So now we have. So we are going to draw a free body diagram to visualize what's going on. So we have basically large vehicle inertia, and then we have small engine inertia, and then we have basically motor on the vehicle side, and then we have engine torque on the engine side, and then we have road load on the vehicle side, and then we have clutch torque equally applied to both sides, but in opposite direction, right? Action reaction. So this is the free body diagram, and if you want to develop a model using this free body diagram, you will end up with this type of model. So you have a dynamic model or vehicle model, and then engine dynamics, and then you have clutch model. Okay. So engine model has these inputs, clutch torque, and firing. Firing is the control input. And then output would be engine speed. The vehicle model takes input torque, which consists of clutch torque and motor torque, and then resulting output is going to be input, the vehicle speed. Okay, and you take a summation of that, and you get delta omega, and that's going to be an input to the clutch model, and you have clutch pressure as a control variable for the clutch model. Okay. Any questions? So far, pretty straightforward, right? So this is a modeling of a mechanical system, but the tricky part is this part and this part. These two are new parts. You are familiar with vehicle model already, okay? Oh, by the way, so there are three control inputs, okay? Firing, control inputs to the whole system. Firing, motor torque, and then clutch pressure. If you look closer into clutch model, this is nothing more than Coulomb friction model. Which you learn from, I think freshman undergrad, physics. So this should be very straightforward. But there's one tricky part. Theoretical model is simple, but when you actually numerically implement this in simulations, it becomes a bit tricky because you have these two states, slip and stick state. So when you lock up, when delta omega equals to 0, then it's in stick state, meaning that two clutches are rotating together, and there is higher friction and this which makes they rotate together. Okay, but then once your torque between these two shafts differs, meaning that once your torque transfer across the clutch exceeds the friction maximum friction torque, then it'll start to rotate. It'll start to generate delta omega, right? And then you move into this dynamic friction region, right? So you learn that from moving this box, right? Same thing, okay? It's just that we're looking at two rotating shafts instead of pushing a box, okay? So when there's a box sitting on a surface, it leads to higher friction, right? But as soon as the box starts to move, the friction drops, because then you are getting into this dynamic friction region, okay? And this creates some complexity because you have these two states and you need to go back and forth between the two models, okay? When it's in stick condition, you have 1 degree of freedom, okay? Because everything is rotating together, right? But when it's slipping, you have 2 degrees of freedom because engine and vehicle is rotating at different speed, okay? So you need to somehow go back and forth between the two. And the problem is that when, what is the condition for these transition? And when you go from this to this state, what is going to be the, you need to introduce new state, right? You need to create these state. And these are not trivial, okay? But luckily in Matlab Simulink, they provide, I think, toolbox that provides this. But for dynamic programming purposes, we cannot accommodate this, two-state model, because that introduces another state, okay? And we don't want that. So usually, for dynamic programming purposes, we need to approximate this model using this kind of approximated function, okay? And then there's this driveline model, which includes transmission, but we're going to assume gear ratio is fixed. So it's very simple. Vehicle dynamics, you guys are already familiar with. Now let's move on to engine model, which is probably the most complicated part. But I'm not going to get into details in this lecture, as it can take quite a long time to explain all the details. But to give you an idea, this is easy, right? This is Euler equation, engine dynamics. It's just summation of all the torque. J omega dot equals summation of torque, and J is here, right? So this is easy. Here's engine generated torque, clutch torque, some losses and some piston generated torque. And this is how the model looks like. So now it gets a little more tricky, right? Complicated. But to give you to summarize what's going on, what we need to compute is this part. So clutch is input, right? It was given from the clutch model. This is given. This is also calculated. This is given parameter. This is model parameter. So we need to compute engine torque, right? And so this is now output we are trying to compute. And to compute this, we need cylinder pressure model. So pressure inside of the cylinder. And then using that value for each cylinder. So we have four cylinder, we're assuming 4-cylinder engine. So we need to compute 4 cylinder pressure for each cylinder. And we need to compute torque for each cylinder. And then you take summation of all of that. And you get total engine torque. So how do we compute cylinder pressure? Well, it's a function of engine speed, intake manifold pressure, and engine crank angle, and then firing command. So those are these 4 sorry about that. So it's a function of these 4 variables, and the inputs are firing command, engine speed, crank angle, and then manifold pressure. Okay. Engine speed, crank angle, and manifold pressure is computed value from the model. And manifold pressure is this intake manifold pressure. So when you have these engines, you have this sort of right. You have this intake manifold pressure, and then you have this throttle. There's some space here that stores energy. Okay, this is called intake manifold. Okay, and then when you open this intake valve, then air goes into this, and this manifold pressure means this pressure, and cylinder pressure means this pressure. Okay. So you need to compute this manifold pressure, which requires some thermodynamic equations, and then mass transfer, mass transfer and energy balance equations for inflow, because you have this intake manifold, you have inlet, outlet. So you have inflow, you have outflow, then you have throttle, right? Okay. So these 2 are the key equations. Okay. So this is engine torque model, and this is intake manifold pressure model. And inside of the engine torque model, this is more details of each model, engine torque model and manifold pressure dynamic model. I don't expect you to understand all the details, like I said, but just hopefully this gives you an idea of what it looks like. Okay. So this is crank angle, the engine rotating angle. So as you can see, when motoring, meaning that there's no firing, okay? No firing. And this is firing, okay? And you can see the pressure changes, okay? When there's no firing, it simply repeats this process. But when there's firing, there's this high peak pressure, okay? So, and under this curve, this is what's moving the engine, okay? This is the work the engine is providing, okay? So this is compression cycle, and this is combustion and working cycle. Okay. Again, manifold pressure dynamics is just mass transfer and some thermodynamic equations. Even more details of intake manifold, intake valve. So how pressure model changes with intake and exhaust valves. Okay, when intake and exhaust valve changes, right, the cylinder pressure model must be changed. Okay, so that's what's happening here. Especially when you start the engine. Okay, when you start the engine. But once you start the engine, then you can just simply follow this crank angle based pressure map. Okay. All right. So let's move on. So this is model validation. This compares the developed model in a Simulink environment, and this was compared with quite detailed model provided by General Motors, and it wanted to basically reproduce or mimic this high fidelity engine model. So, and you can see that they actually, their behavior is quite similar. Okay, the torque, and then the speed, engine and vehicle speed, and so forth. Okay. So, any questions so far?
Oh, can I?
Some of these. So we're trying to identify, organize our model and the problem, control problem. So here, so what are the states? Right? We have engine speed, crank angle, and intake manifold pressure. So these three have dynamics, right? Key dynamic states. And then we have three control inputs, okay? Which is clutch pressure, firing, and then motor torque. So motor torque. And then for this for this problem formulation, we are going to make some assumptions and let these three variables become a predetermined parameters, okay? Let's assume driver demand is this value, and let's say, you know, vehicle speed and gear ratio is fixed, then transmission input speed is known, and let's say initial crank angle, engine angle is also known, okay? Then what do you see? Do you think we can solve this using dynamic programming? Probably, in theory, right? But the problem is there are many states and control variables, and there is this famous curse of dimensionality, meaning that the computational load explodes with the number of state and control variables. Okay, so if you want to apply DP to solve this optimal control problem, you need to somehow reduce number of states and control variable, right? Do we absolutely have to keep these state variables and control variables? Well, let's talk about that soon. So, by the way, this is just to give you an idea of what the solution would look like. This is just conceptual drawing to help formulate the DP problem. So X being time and Y being engine speed, and we want to increase engine speed as fast as possible, right? But without too much delta torque, which is what we just mentioned earlier, you know, Nellin asked, right? The torque demand minus actual torque, right? So this is delta torque, okay? And we want to make sure the output torque meets the torque demand, okay? So this is, like I said, this is just, you know, conceptual solutions, okay? So we probably have absolute minimum time, right? If you just, you know, apply maximum pressure on the clutch, then you will start the engine as fast as possible, but you will have a lot of delta T, right? And then there's a perfect disturbance rejection solution, meaning that minimum time without sacrificing delta torque, okay? And then you have some trade-off solution somewhere in between these two, right? And then if you want to even reserve some torque, then you can also have slower solution, okay? In case driver asks for more torque, okay, while you start the engine. So to find these solutions, I had to formulate two separate problems. You know, one for solution 1 and 2, and 2 for solution 3 and 4. Okay. And because for 1 and 2, delta torque is something we can compromise, okay? Something we can compromise. But solution 3 and 4 is something we are not going to compromise. You know, we're not going to compromise delta torque. Delta torque is always equal to 0 for here. Instead, we're going to even ask for more torque reserve, okay? And we need to apply these constraints. And this is, so this is the actual original optimal control problem we want to solve, but in order to numerically implement this, we had to modify that original problem into in the form of computer can understand, right? To numerically implement. So this is modified version of that. You can see the cost function is modified. Where initially this was time, right? Where this was, you know, integral, right? And this is final time, right? But to numerically implement that, we need summation, right? And we actually needed extra terms to make the solution you know, more practical. Okay. For instance, we want to make sure you know, clutch pressure doesn't oscillate, doesn't fluctuate too much. You know, pressure can be very noisy, right? The solution can be very noisy. And then we also want to reduce mg torque, motor torque. So we need these very details when you actually numerically solve these problems. Okay, these are some techniques, and this is the results. Okay, this is direct DP results. Okay, so nothing is modified. This is raw data. So, and you can see very similar behavior from what we initially imagined, right? So this is the absolute minimum solution, but there's a lot of torque delta torque, and then this is the perfect disturbance rejection solution, and there's a trade-off solution, and then there's a torque reserve solution. Okay, and you can see you get slower solutions as you limit the power flow into the engine. So in practice, probably, somewhere around this blue line is going to be, a practical solution. Okay. And you're looking at manifold pressure. Because the engine rotates faster, manifold pressure drops faster. Okay. And you can also see that you can start the engine faster because you apply higher clutch pressure, and as you lower clutch pressure, you start the engine slower. Okay. And then note that when you move across from negative delta omega to positive delta omega, you see these spikes. Okay. And that's because we used approximated clutch model. Okay. I'm not going to get into details of that, but anyway, yeah. So you're looking at more detailed plot results of solution 4 with torque reserve, some torque reserve. So this is the slowest and quite conservative approach. And you're looking at the results. So you're looking at some clutch pressure, firing command. You're looking at torque. You're looking at motor torque, clutch torque, and then engine speed, delta omega, and so forth. Again, this is raw data. This is DP results. Okay. So this was quite interesting, and DP was able to find the solution that actually makes some sense. But this spike, this noise, was something we didn't expect, and that's because of the approximated clutch model. Okay. And what I mean by that is near zero slip. Okay. We are using this approximated clutch model, so we need to apply large torque to create friction. Okay, because when for zero slip speed, the mu also becomes zero. It goes across this zero value. Okay. So somewhat to summarize the results, you're looking at initial X being initial clutch pressure, Y being engine start time. And you can see with increasing clutch pressure, you get lower engine start time, and vice versa, right? And also with increasing torque pressure, you see slower solutions, slower engine start time. And I also tried to solve this problem using variational approach. So does this look familiar, right? So first we want to find the necessary conditions, right? And I was able to drive up to this necessary conditions, but these equations are not solvable right? Analytically. We could either solve it numerically, but global optimality is not guaranteed. Okay. But if we break down the problem into smaller problem, I was actually able to solve this analytically. But I'm not going to talk about this in detail. I think time is almost up. So let me move faster here, okay? So please take a look if you're interested in, you know, how optimal control problem is formulated for engine start control problem, okay? And this is analytical solution, analytical approach. And you can see this is quite similar to the numerical approach, the DP solution. Okay. So the whole point of doing this was two things. Just like fuel economy, we wanted to find out the fuel potential, the limit. What is the theoretical limit of the engine start control problem? How fast can we start the engine without sacrificing power demand, right? Without compromising power demand. So, and so we formulated simplified optimal control problem and solved it by DP, and we were able to find the solutions, and we were able to see the full potential of that. Also, we also want to eventually design a controller, right? Real-time controller. And can we learn something from DP solution? Okay. So this slides show that, and for the time availability, I'll have to move fast. Okay. So this is the proposed control architecture. So we have this. This is the plant, where this is the plant itself, and this is the actuator of the clutch dynamics, which we neglected for DP problem. But we need to, for real-time control problem, we need to consider actuator dynamics. So what we need to design is that we need to design the clutch pressure controller, and we need to design a motor controller, and we need to design the controller that outputs reference pressure. Okay. So, and this architecture is proposed because in many applications, if you formulate this as a inner loop, outer loop formulation, meaning that this controller, this actuator controller, focuses on tracking clutch pressure, the reference pressure, and you can decouple designing this controller and this controller, assuming this is faster than this dynamics. Okay, and then motor controller can focus on the NVH problem. So filter out some of the fluctuations, and also focus on canceling this clutch torque, okay, clutch pressure clutch torque induced by the clutch pressure, okay? Otherwise, it will be transmitted to the drive line and the wheel, and passenger will feel it, okay? So now what's left is this outer loop controller, which outputs the reference pressure. What should be the pressure command, pressure reference? And that DP solution can help, right? So, and this, but the main difference between this problem with fuel economy problem is that this is actually time invariant, and we can directly implement. So for a fuel economy problem, it was time varying because the power demand and vehicle speed was different as a function of time. So it was time varying solution. But here, because all of the state is here, this is time invariant policy, control policy. So we can directly implement. So this is the plot of the DP solution. So this was a trajectory plot, okay, of the DP, meaning that you give initial conditions and you apply DP policy, and this is the trajectory that's generated from the DP controller. And here, this is the policy itself, okay, meaning that the output is clutch pressure as a function of engine speed and manifold pressure and time step K. And you can see that with a different time step K, the policy doesn't change, right? So we can directly implement this. This is time invariant, okay? And we just need to remove this noise, this spike near delta omega equal to 0. Okay, so we remove that. You can see that here. This I had to modify. Okay, this was done by engineer. Okay, and that's because of the model approximation. Anyway, so this is the resulting control policy, and this is the resulting simulation results. And you can see this is identical to the solution we saw, I think, right? This one, right? Except for this part, right? The spike, because we removed it. All right, I think that's it. Any questions?
Yes.